Hello guys, welcome to eSpark Tech Academy channel. Now we will be going through Norton's theorem as well as its example. Already in previous lecture I have covered Norton as well as Thevenin's theorem. Now we will be going in some sort of detailed examples because in your exam difficulty may vary from easy, moderate and little bit harder or difficult ones. That's why we will be going through other example on Norton's theorem. Here I will draw the given circuit diagram. Here it is given as 40 volt. Here it is given as 20 volt. The resistance values are 20 ohm and 10 ohm. Now this is the point A and B where we will be calculating the Norton short circuit current. Now they have told us to determine Norton's equivalent. Now in such cases when they ask Norton's equivalent, we have to first reduce this circuit in ISC parallel resistance, which will be Rn or equal to Rth, and it will be the points where load resistance will be connected. Now this is the Norton's equivalent circuit diagram which we have to calculate. Now first of all, what you will do in this case, first you will calculate the RTH. RTH, you know, while calculating RTH we have to replace these voltages and any kind of current sources with their internal resistances. Here one thing which I have to mention is voltage source is replaced by closed switch, means short circuited, because voltage source is having nearly zero resistance internally, means internal resistance, zero internal resistance. And if there would be any kind of current source, here is replaced by open switch, which is nothing but open circuit, you can say, for current source, and here it will be equal to infinity internal resistance. Now we have to calculate this RTH. So what we will do is, first we will short circuit this voltage source. This will be 20 ohm and 10 ohm already given. Now we have to calculate the RTH. RTH will be nothing but parallel combination of 20 ohm resistance with 10 ohm resistance. It is nothing but 20 into 10 divided by 20 plus 10. It will be coming as 6.66 ohm. Now this is the first case. Now what we have to find is, we have to find the current through these terminals A and B. When we short circuit these points, now I will be drawing a circuit. First note down it. The RTH. Now we will be finding the ISC. Or you can say IN. Now IN equal to ISC is equal to, the circuit diagram will look like here 40 volt already given, here 20 already given, here the resistances are given as 20 ohm and 10 ohm respectively, and this is the point A and B through which we have to find the current. This is nothing but IN, which we have to calculate. Now what you will do is, you have to first calculate these currents which are flowing. This may be I1, this may be I2. First, what will be the I1? I1 is nothing but a voltage divided by this resistance, which is 40 divided by 20. You will get as 2 amps. 2 amps. And here I2 will be nothing but 20 divided by 10. It will be 1 amp. As these currents are flowing in this direction, IN will be simply applying KCL. IN will be I1 plus I2 here. It will be nothing but 3 amperes. 3 amperes. Sorry. 1 minute. Is the mistake. This is 2 to 4 amperes. You can see 4 amperes. It was a silly mistake. It is 4 amperes. Now what we will do is, we have just now calculated our Rn, which was 6.66 ohm. Now we will draw this kind of circuit, the Norton's equivalent circuit here. Norton's equivalent circuit. What it will come as, you will draw current source in parallel with this Rn. Here the Rn is 6.66 ohm, current source is 4 amperes, which is IN, and this is nothing but the point A and B. You can say this is the load which is externally connected. This will be the solution. Please note down it carefully. It was little bit tricky question because here we have also made use of KCL to find out the Norton's current, the short circuit current between the points A and B when these both points are short circuited. Now we will be going to see the maximum power transfer theorem. What actually the maximum power transfer theorem is and how we determine the theorem. Now any voltage source maximum power transfer theorem. It will be RL will be the load resistance, RTH will be the open circuited Thevenin's resistance, and this will be VTH, the open circuit voltage across the points. Let it be A and point B. Now in this case the maximum power will be transferred only when max power, you can say max power can be transferred in the circuit when its RTH, it is the circuit resistance, equal to load resistance. It will be variable in order to make these two quantities equal. Here RTH should be equal to RL, means RL should be equal to RTH in either way, you can say. That's why we calculate the maximum power as VOC square divided by 4 into RTH, or you can say here RTH equal to RL. This is the formula for maximum power transfer theorem, and this is the condition of maximum power transfer in DC circuit. Now based on this we will be finding the examples. First of all, here basic equation I will tell you. In this case, when we calculate the current I will be nothing but the voltage VOC divided by RTH plus RL. This is the I, and the current flowing through this RL will also be I. Hence power P load equal to I square R. In this case this I is nothing but small I, where VOC divided by RTH plus RL bracket square into the RTH, you can say, or you can say RL in this case, because of load resistance. When you calculate this and differentiate with respect to RL, when let it be equation 1, differentiate with respect to RL, you will get it as dP by d RL is equal to VTH square, or you can say VOC in this case, VTH square into RTH plus RL square minus 2 into RL into RTH plus RL, you can see, and it is nothing but divided by this RTH plus RL raised to 4. When you solve these, you will get the values as VTH square minus RTH plus RL square minus 2RL RTH plus RL is equal to 0. We will equate this dP by dRL equal to 0, as this denominator will be multiplied by 0, hence denominator will become 0 in this case. Now by solving this, you will get the values as RTH plus RL square equal to 2RL RTH plus RL. Now from this example you can say it as RTH plus RL is equal to 2 into RL. Now RTH equal to RL, just interchanging this 2RL minus RL will become RL and RTH. Hence we have proved the maximum power transfer condition. Please go thoroughly through this. Just what we have done here is we have just differentiated, took the derivative of the above equation number 1, and with respect to RL we have differentiated it. Hence just by using the division rule in case of derivatives, we have found this answer. Thank you. Please go through it very well. Now in next lecture we will be dealing with maximum power transfer theorem problems. Thank you for watching eSpark Tech Academy, and please like and subscribe the channel. That will motivate me to give you more ideas, more tricks related to any electrical analysis circuit or any kind of topic, any machines and everything. We will be dealing one by one as per your syllabus.